All right. So we got a few problems up here to do for today. This is just expanding on the stuff that we did on Wednesday. So it's not using anything new, any new lectures or anything like that. But just sort of want to look at some of the stuff we've been doing. All right. So, actually, I need one more thing here. I've got my little stand here. All right. So in the first question here, problem 1. Oops, why am I writing in green? Right, in problem 1 here, we want to find a Maclaurin series for this function right here. Right? Where here, k is allowed to be any real number we want. All right? So, well, what do? Let's just write this out. So we're going to do the, I should have used a different number there instead of k. Let me switch this to, oh god, why did I mix these up? Let's call this r. So it's r for any real number r. I got a little too carried away with the k's there. All right. So what we're going to do is our usual. All right, so we're going to make our chart as we always do. And try and find a pattern to these. All right. So when k is 0, obviously the function doesn't change at all. And so if we plug in x equals 0 here, this is just 1. All right, no big deal. Now, if k is 1, we have to take a derivative. So we get r times 1 plus x to the r minus 1. But now the nice part about this is, if we plug in x equals 0, this is just r. All right. If we take the second derivative, we have r minus 1 times 1 plus x to the r minus 2. Right? And so we get r minus 1 when we plug in x equals 0. Right? Because each time, this is just 1 to a power. So if you keep following this trend, right? r minus 1, r minus 2, 1 plus x to the r minus 3. Right? And so here we have r minus 1, r minus 2. And, it's probably not too surprising at this point to see that, all right, well, what are we going to get? So the pattern here, fk of 0, this is going to be r times r minus 1, or maybe I shouldn't write this out with dots. r minus 1, r minus 2, dot, dot, dot. Now, what does this end at is the question. Well, notice here how this always ends at r minus a number that's 1 higher or 1 lower than this. So it's r minus k, but that's 1 too low, so we have to add 1 back. Right? Okay, so this is the pattern that this holds on to here. Now, it's important to specify that this actually only holds for k at least 1. If k is 0, this pattern doesn't really make sense. But we'll handle that in a moment here. Right? So, all right. Now, when we have a pattern like this, right, where we kind of start at a number and multiply numbers going down, we know this is like almost a factorial kind of thing. So here if we have r minus 1, r minus 2, dot, 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 r minus k plus 1. What we would really like to do is just add in the rest of these, r minus k, all the way down to 1, right? Because then this is just r factorial. Well, not too hard to fix here. All this stuff that we just added, r minus k, all the way down to, well, 1, that's a factorial itself. So this turns into r factorial over r minus k factorial. Not too bad, right? So then ck, remember this is fk of 0 over k factorial. This turns into r factorial over k factorial r minus k factorial. Right? Now, one really cool thing about this that I want to point out is this expression up here, it seems a bit odd if k were 0. But here, k is allowed to be 0, because if we plug in k equals 0, we get r factorial over r factorial, which has got to be 1, which is what we want, right? So we're good to go. Right? So this expression right here, this holds for k greater than or equal to 0. So what that means is this expression, the Maclaurin series for this expression right here, is simply k, or the sum from k, oh god, this is supposed to be an r. The sum from k equals 0 to infinity of r factorial over k factorial r minus k factorial. And then here, this is x to the k. All right. Now something, some of you may know or be familiar with is this expression right here. This is actually a certain what's the word I want? This is a special type of number in mathematics. So it's known as a binomial coefficient. Right? And it's known as a binomial coefficient because, well, 1 plus x, this thing is what we call a binomial, right? Two things added together. And then here we're taking that and raising it to a power, so these are coefficients of a binomial raised to a power. Hence we call them the binomial coefficients. And what the way we write that is these two numbers on top of each other, no line in between. This isn't a fraction, right? So we write that x to the k. Right? So this thing right here, we usually pronounce this as r choose k. Right? So another interpretation of this number, which any of you have done some kind of like probability counting kind of stuff before, this stands for sort of, you have a list of, think of it like a box full of r different items, right? Then the way you compute this, the k stands for how many of those items do you want to pull out, right? So there you go. All right. So this notation here, there's ways to make sense of this stuff when r is not an integer, but our definition here works for, it makes sense when r is an integer. If r is not an integer, then you still compute this same thing here. Okay. All right, any questions? Actually, let me just say, R choose K can always be interpreted to mean, R times R minus 1 times ... times R minus K plus 1. Right? You can always interpret it in this way. So that way, this expression makes sense for numbers that are not integers, right? Numbers are that are not 2 or 4, something like maybe if it's 1/2 or something like that. Okay. So let's go ahead and go on to number 2 then. So the reason I bring that up is it's really relevant for this here. All right, so I want to find a Maclaurin series for this function here. So this function here, this is actually something we can apply the binomial theorem to. Or sorry, the binomial series, which is the thing we just came up with. All right. I'm just double checking something real quick. To make sure I wrote this down correctly. All right, awesome. Oh, nope. See, I did get something a little bit wrong. This is why I wanted to double check. This is the numerator. The denominator is still k factorial here. There we go. All right. So, if we're trying to compute a Maclaurin series for a function like this, what we're going to do is simply say, well, let's manipulate this a little bit. All right. So 1 over square root of 4 minus x. This is, first things first, this is 4 minus x to the negative 1/2. Right? So this is almost ready to be hit with the binomial theorem, with the binomial series, sorry, right? The one we just came up with, except for it really needs this 1 here. So let's fix that. Right, we can do the same kind of thing we did last time. What did we do this with? I'm blanking on the specific example. Oh, the geometric series stuff, right? We needed a 1 specifically. So here, if we just factor out a 4, we get this. 1 minus x over 4. The minus 1/2. Right? And so 4 to the minus 1/2 is, actually it's it's 1/2. So this is 1/2. I'm going to do a little extra manipulation in here. I'm going to write this as 1 plus negative x over 4 to the minus 1/2. Right? Now that I have that, we're just going to apply our last example, our last problem here, and say this is 1/2 of the sum from k equals 0 to infinity of negative 1/2 choose k. And here, it's going to be this expression to the kth power. Right? This is what goes inside the parentheses here. Right? So if you want to simplify this sort of to the nicest thing you can, it's going to be something like this. K equals 0 to infinity. Negative 1/2, choose k. Negative 1 to the k. X to the k. Now down here we would have 4 to the k, but since I have this 2, I'm going to write this as 2 to the 2k plus 1. Right? And this honestly is probably the nicest way you're going to be able to express this this Maclaurin series is with these binomial coefficients. Now, of course, you know, it's kind of a weird thing to leave there if you're trying to compute this. So it's always possible to just abandon the summation notation like this and just write out terms. So like here, what we would do is plug in 0, right? So if we plug in 0, anything choose 0 is 0. Or sorry, is 1. So, so the first term will be 1 times 1 times 1 over 2 to the 1, right? Plus, plug in 1. Now, this binomial coefficient here is going to turn into negative 1/2, right? Times negative x over 2 to the 3rd. Okay? And then the next one, so now we're going to take negative 1/2, and we're going to subtract 1 and multiply the next number, right, which is minus 3/2. And then here we have, let's see, negative 1 squared, so this is 1 times x squared over 2 to the 5. Right? And then so on. Right? This will keep going on for a while here. Right? So, you know, it depends on sort of what you're really looking for, what you want the answer to, what you want the final form to be. I honestly think this here would be the better way to leave it. All right. Any questions there? Okay, cool. Let's go ahead and look at the third problem here, which actually might fit right here on this page. So number 3, we want to find the exact value of this series. So sum negative 1 to the k, pi to the 2k over 6 to the 2k, 2k factorial. All right, so what's going on here? How can we find this, the value of this series? Well, the goal will be to make this look as close as possible to some series that we actually can recognize. Right? Any thoughts on what this kind of looks like? So those 2 k's there should kind of give you a hint. So if we rearrange this a bit, we'll put the -1 to the k here. These two, since they're both to the 2k power, let me write it like this. Right, does that give you a hint as to what this should be? So this is the Maclaurin series for cosine, with x replaced with pi over 6. So this is cosine of pi over 6. In other words, the sum of the series is √3 over 2. Right, so that's one of the really neat things that power series allow us to do, is if we can recognize the series as the power or the Maclaurin series or the Taylor series for a given function, then we can use that to compute the value of the series. Now again, just like with the geometric series stuff, or actually being able to find the formula for the partial sums, in the grand scheme of things, this is pretty rare. To be able to actually figure out, oh, hey, this is this power series. Right? It's not a very common thing to be able to do, but it is a thing that we can do sometimes, which is pretty cool. All right. So let's look at problem 4 here. We have another series of things here. So 1 minus ln of 2 plus ln of 2 squared over 2 factorial minus ln of 2 cubed over 3 factorial plus dot dot dot. Now, does this look familiar at all? Does this look like any kind of thing you would be able to write as a power series? So it's an alternating series starting at 0. So we got this. And we're getting higher and higher powers of ln of 2. We got this. And the bottom is always tracking with the power. So it turns into this series. Does that look like something we can do anything with? Well, to do this one, we actually need to combine the numerator here, because this doesn't quite, it looks close to a Maclaurin series that we know, but it's not quite there. So if we combine this inside here, though, this should look to you exactly like the Maclaurin series for e to the x, which means, well, this is e to the negative ln of 2. And we can compute the exact value of that, which is minus a half. Or sorry, just a half, 1/2. No minus, just 1/2. Right? All right. So any questions there? All right. So let's look at the next problem. Now, in the last video, for the lectures, we talked about different using Taylor polynomials or Maclaurin polynomials as ways to approximate a function, right? So in single variable calculus last semester, you learned how to find the tangent line to a graph, right? And that tangent line to a graph, it functions as sort of an approximation of the function, a linear approximation, if you will. Right? It's what we would call a first order approximation. Sorry, my headphone batteries are dying here. There we go. All right. So, by using higher and higher degrees of the Taylor polynomial, we can get better and better approximations. So, here we're trying to estimate square root of 101. Okay? So, well, this looks like we took f of x equals square root of x, and we plugged in 101. Right? And then we want to approximate that. Well, okay. So let's look at different approximations of this here. And the way we're going to do it is we're going to take the linear Taylor polynomial, which again, the graph of that's just going to be the tangent line. We're going to take the quadratic Taylor polynomial, and then we're going to take the cubic Taylor polynomial. So let's go ahead and compute those parts of the Taylor polynomial now. The question is, where do we want to center this at? Right? That's the interesting part of this. Where to center your power series. Right? So in this case, what do you think is a good place to center the power series? If we're trying to estimate the value of 101, we want to center for the series as close to this as possible. Right? As close to 101 as possible, where we can get sort of like a nice value of the function and its derivatives. Because remember, we have to make this series, right? So we want to estimate this thing we can't compute by building it out of pieces we can compute. So what do you think would be a good place to center this series? Right. So a good place to center this is the closest value where f of x makes sense, or where we can compute it by hand. So notice, if we use 100 as the center, we can compute the square root of 100. So we want to compute a Taylor polynomial centered at a equals 100. Right? So we're only going up to a cubic here, so we can actually use the same kind of chart that we always do. Right, but we're only really worried about the first three terms. Or sorry, first four. Because we want k equals 0, 1, 2, and 3. And that's it. Right? So k equals 0, of course, we have square root of x. and then plug 100 in, and this is 10. Take the derivative here, we're going to get 1/2 x to the minus 1/2. All right, so this is, let's see, 1/2 times 1/10. So this is 1/20. All right. Take the derivative again, we're going to get minus 1/4 x to the minus 3/2. Now again, the nice thing here is, we're not really worried about, looking for a pattern this time, because we're only going to compute a few terms, right? So simplify as much as you can. It will save you time. Right here, so we have minus 1/4 times, this is actually going to be 1/1000. Is that right? Yes, this is right. Right, so this is minus 1/4000. I know, it's getting a bit ridiculous, right? But it's going to make sense. Right? Take the derivative again. We're going to have 3/8 x to the minus 5/2. Plug in 10. We get 3/8 times, let's see, this is 1, 2, 3, 4, 5. So 100,000. So this is 3/800,000. Right? So now we have all of these first 4 Taylor coefficients. So now let's do each approximation. So the linear approximation, right? We're going to take the first degree Taylor polynomial. So let me say f of x, this is approximately equal to what I'll call this t1 of x, to stand for the first Taylor polynomial. Right? And this is simply f of 100 plus f prime of 100 times x minus 100. Right? These are the first 2 terms in the Taylor series for this. Okay? So this will be 10 plus 1/20 x minus 100. Right? So what we're trying to approximate is the square root of 101, so plug in 101 here. So f of 101, it's approximately t1 of 101, and this is 10 plus 1/20 times 101 minus 100. In other words, 10 plus 1/20. Now 1/20 is 0.05, so this is 10.05. Right? So that's what we have here. This is an approximation of square root of 101. Right? That's the linear approximation. Let's move on to the quadratic approximation. Okay. The quadratic approximation, in this case, we'll say f of x is, this time let me call it t2 of x, to stand for the second degree Taylor polynomial. All right, so this is f of 101 plus f prime of 101, x minus 100, plus f double prime of 101 over 2 factorial x minus 100 squared. And now we compute this. Well, let's actually write out what this is. So this is 10 plus 1/20 x minus 100 plus, right, so f double prime of 100 we said was negative 1/4000. And then we have to divide that by 2 again. So this is actually going to be minus 1/8000 x minus 100 squared. And this is our quadratic approximation. Now again, this being centered at x equals 100 means that at x equals 100, of course, we get the exact value of f of x. And then as we move away from x equals 100, the approximation gets slightly worse as x goes further away. And eventually it becomes terrible, right? But it depends on how high of an approximation you take, how high of a degree, and it depends on the radius of convergence. If you leave the radius of convergence, you're just kind of hopeless. But if you're close by and you're within the radius of convergence, then you're going to get some pretty good approximations. All right, so let's go ahead and compute this. All right, let's see here. So f of 101, this is approximately 10 plus 1 over 20 times 101 minus 100 minus 1 over 8,000, 101 minus 100 squared. Right, so that's 10. Again, this is plus 1 over 20. This is going to be minus 1 over 8,000. So 10 plus 0.05 minus 1 over 8,000 will be a finite decimal, but I don't know what that would be offhand. Something with the 125 in it. Okay, so minus 0.000125. Right? So it's 10.05. Oh, sorry. Not quite. 0.4. Let me do it this way. 1 plus 0.05 minus the answer. 0.49875. There we go. So what we now find is that the square root of 101 is approximately 10.049875. That's what this quadratic approximation does. Right? So let's go one step further, look at the cubic approximation, and then we'll see just how good these approximations are. Right? We'll use a computer or a calculator to compute sort of the exact value, if you will. And we'll see sort of maybe how many decimal places it's good up to. Right? So start making some guesses. How good do you think this linear approximation is? How good do you think this quadratic is? Right, let's look at the cubic approximation. Okay, so cubic. Okay, so here, f of x is approximately t3 of x. So this is your third degree Taylor polynomial. Right, this one's going to be a little bit of writing here. Come on. Plus f double prime of 100, 2 factorial x minus 100 squared. Ran out of room, of course, so I'll just add here. Plus f triple prime of 100, 3 factorial x minus 100 squared, or cubed. Right? So, big surprise, we're going to do the exact same thing. Write out what this is. So f prime, or f of 101, or actually, sorry, let's write out this polynomial. So this is 10 plus 1 over 20, x minus 100. 1 over 8,000. X minus 100 squared. And then let's see, what is our cubic coefficient? 3 over 800, 3 over 800,000. And we need to divide that by 3 factorial. So that's going to be plus 1 over, it's actually 1.6 million. X minus 100 cubed. All right. So that means f of 101, this is approximately 10 plus 1 over 20 minus 1 over 8,000 plus 1 over 1.6 million. Whatever that is. Right? So that's 10 plus 0.05 minus 0.000125. I think that was it. Right? Did I get that right? 125, yep. And then what are we adding back? 1 over 1.6 million. So this is 1, 2, 3, 4, 5, 6, 2, 5. Oh, no. We need more. 1, 2, 3, 4, 5, 6, 7. There we go. 2, 5. Okay. There you go. So now we add all this stuff together. So we'll do that. We'll add 10, add 0.05, subtract 0.05. And so this is 10.04987,563. Right? So this is saying that square root of 101 is approximately this number. Right? So we have these varying approximations here. So we had the linear, the quadratic, and the cubic. This one was 10.05. This one was 10.049875. And this one was 10.04987563. All right. So what do you think? When we go to compute the actual square root of this, what are we going to get? Well, let's pop this into the calculator. Calculator tells me. Actually, let me do this in Mathematica so I can try and get many digits. Calculator is going to cut off at some point. All right, so how many digits do we have here? We have 8. So let me try and get it with 10 digits. Is this enough? 1, 2, 3, 4, 5, 6, 7. We'll do one more. Okay. So, accurate to 10 decimal places, square root of 101, so this is 10 decimal places. This is 10.04987,56211. Right, so you can see that the linear approximation isn't that bad, right? I mean, we're off by less than 100th, right? Less than 1 over 100. It's not too bad. In fact, less than 1 over 1,000. It's really not that far off. But look at when we move from linear to quadratic, right? It literally is just a truncation of this, right? I mean, if we rounded to the 6 decimal places that this has, this is too low, but it's exactly the same. And if we move on to the cubic, which adds in 2 more decimal places for us. All right, so this 3 and this 2 differ, but these 6s match up, as does everything before. So you can imagine if we took a, what is it called? A quartic approximation, a degree 4, this would get even better, right? So these kinds of approximations using Taylor series are really wonderful. Really love it. And this is, this is how your technology is going to compute these things. It's going to take some high series like this, high degree Taylor polynomial. There's a way to estimate the kind of error that you're going to get when you do this. Yeah, I'll let you read that in the textbook. I believe it's in there, how this works out. But it's really quite awesome how these approximations work. I know we started like 3 minutes late, so what the heck, I'll just go ahead and do these for problem 6 here. So problem 6. So here we have e to the x cosine y, xy, right? And we want to find linear and quadratic Taylor polynomials to approximate this, right? So to do that, we need the gradient and we need the Hessian. So here, we'll go ahead and use Mathematica to do some of these derivatives. Right. So let's see, gradient of f So our gradient of f at xy, this is going to be e to the x cosine of xy minus e to the x y sine of xy times negative e to the x sine of xy. Right. And then the nice part is we only want to compute this at x equals 0, y equals 0, because this is where we're centering our series. So plug that stuff in, gradient of 0, 0, and we simply get the vector 1, 0. So that means the linear polynomial f of xy, this is approximately, which I'll call t1 of xy. Oh, we actually need to plug in 0, 0 into the function, which is 1. Right? So this is going to be 1 plus 1, 0 dot product with x minus 0, y minus 0. Which in this case is 1 plus x plus y. Right? So remember here, if we graphed this function, say z equals this is the tangent plane at 0, 0. Right? And so just like we did in the last example, where we were approximating, plugging in different values, this is going to be a somewhat crude, but an approximation of values near the origin for this function, f of xy. Let's move on to the quadratic now. So we need the Hessian. Which is, remember, all the second derivatives. I'll leave this off. All right. So let's go ahead and use Mathematica to compute this, but I'm going to just use it to compute it and automatically plug in 0, 0. Just to save some time here. All right, so let's see, this one's going to be 1. This one is going to be 0. Did I get that right? Make sure I clear this. Okay, cool. All right, that looks fine. Just trying to make sure I got everything correctly here. Okay, so then these are both 0. Interesting. Okay, so remember the second degree f of x comma y, right? This is what we call t2 of xy. And remember, this one is going to be, this one will be f of 0, 0 plus gradient of f at 0, 0 dot product with x comma y. And this next one, if you think about these in terms of matrices, you want to write it this way. X, oops, I forgot the 1 over 2 factorial. 1 over 2 factorial x, y times this Hessian times this. Right, so you want to write out this product in this way. And so if we compute this, so here we know this was 1 plus x plus y, because that first part will always be the same. Then we just add on this additional part here. And if you multiply this out, all we're actually going to get is plus 1/2 x squared. That's interesting. All right. Any questions there? All right, then. Yeah, so kind of interesting how that worked out. I actually didn't expect there to be no y's in the quadratic part. Yeah, so those are linear and quadratic approximations of a multivariable function. So some pretty interesting stuff here. And, just like last time, like if you wanted to approximate this function at, say, I don't know, 0.1 comma 0.4 or something like that, you could just plug those values of x and y into either this linear or this quadratic approximation, and that would give you how the function's changing there, or the value of the function there. All right. So I will take a break for a bit, and then we'll be back for round 2. So thanks for watching. All right. So, problem session today. The problems today, they're using some of the content from the lectures that we didn't use in yesterday's problem session, and also just kind of expanding a little bit on the topics from the last set of lectures there. Just sort of talking about some of the uses of all that stuff. So, let's go ahead and get started here. The choice of K in problem 1 was really a little bit unfortunate. So I'm going to change that number real quick to R. So we want to find a Maclaurin series for this function where R is any real number. Right? This just means R belongs to real numbers. That sneeze took a minute to come through. All right. So we want to try and compute this series here. So, well, if we're going to try and compute a Maclaurin series for this, let's start taking derivatives and seeing if we can establish a pattern. So we'll plug in different values of K. We're going to look at the derivatives. And we're going to plug in 0. Right, because this is a Maclaurin series. Right? So when K is 0, well, we just have the function itself. And so if we plug in 0, we're just going to get 1. All right, woohoo, exciting. Cool stuff. All right, well, let's take the first derivative. Right, so that means an R comes out. We get 1 plus x to the R minus 1. Plug in 0. All right, now we get an R. A little more interesting. Take the second derivative. Let me start piling these up in this direction. R minus 1 times R times 1 plus x, the R minus 2. No, actually I changed my mind. R minus 1. Keep doing it this way. So plug that in. We have R times R minus 1. Take a third derivative. R minus 1, R minus 2, 1 plus x to the R minus 3. So when we plug in 0, we get R minus 1, R minus 2. You can probably see where this pattern is going from here, right? The next one will be R minus 1, R minus 2, R minus 3, right? So I don't really want to write this part out. So we can establish that the pattern here for the kth derivative at 0 is R times R, not plus 1, R minus 1 times R minus 2 times ... Now what does this end at? Right? If we take k derivatives of this, what is the last term here going to be? What do you think? Obviously, it should be R minus something. What do you think?
R minus parentheses K minus 1?
Yep. So if you do R minus K minus 1, you'll get this. Usually we'll distribute that out and just write it as K plus 1 here. Right? But yeah, that's exactly what this is. This is R minus K minus 1. Because if you notice, this number here is always 1 less than this number right here. Right? Now this looks a bit funky if k is 0, because then it looks like you're multiplying r as the values go down until it reaches k plus or r plus 1. So this formula, it kind of makes sense as long as k is at least 1. And then, the 0th derivative at 0, we're just going to understand this to be 1. All right? So it's a bit of a weird thing, but since this number is bigger than that one, we would just say, okay, this is 1. And this is kind of the same logic behind saying that 0 factorial is equal to 1. It's just sort of what we need for it to work out. Anyway, speaking of factorials, though, this is, this is fine. We can understand this pattern, but it would be nice to write this in a more condensed way. And we can do that. Right? We can do that by saying, all right, I changed that to black, but by saying, all right, well, I recognize this pattern here as being sort of like half of a factorial in some sense. But if I want to make this top actually be r factorial, I need to add in some things like r minus k minus 1, all the way down to 2 times 1. Right? But I can't just add something in. Right? Whatever I add on here, I also have to divide by it. Otherwise, we're changing the expression. Let's put that down there. So how can I rewrite this thing that I just made here? How can I rewrite this in a simpler way now using factorials? What does this turn into? Top here, we have numbers 1, 2, all the way up through r. Top should just be r factorial. What about the bottom? A nice r minus k factorial.
R minus k factorial?
Yep. So, whenever you have this like list of numbers from like a number down to a certain point being multiplied together, this is sort of where the beauty of factorials come in, because we can just fill in the missing pieces and then just divide by that extra stuff we added in. So when we actually want to write down the Maclaurin series then, right, so this is going to be k equals 0 to infinity. This is our fk of 0, the kth derivative at 0. And then we have to divide this by k factorial. So remember here, this is fk of 0. When we divide this by k factorial, we see something like this. Does this expression right here look familiar to anyone? It may or may not, depending on sort of what math you've done in the past. If you're currently taking Math 220, I reckon this is something you should recognize, though. So the way we write such a thing is we write these two big parentheses and we write an R on top and a K on the bottom. Right, so there's no fraction or anything. This kind of looks like a 2x1 matrix almost here. So this thing right here, this is what we call, the way we read this normally is R choose K. Right, this kind of stands for, if you have a box of R things, how many ways are there to choose K things out of that? Now that analogy, gets a little more loose when R is allowed to be any kind of real number. But again, all this expression means is just, this thing right here. Right? Or sorry, this whole thing. This divided by K factorial. Right? So for us, we're going to call this the binomial coefficient. So again, this is the Maclaurin series for this function here. Oops, that's supposed to be to an R. Yeah, so this stuff in the pink circle is, we abbreviate it by this. So just a little aside, just to sort of redefine this. If if R is an integer, then this all kind of makes sense. If R isn't an integer, how do you compute something like 1/2 factorial? Well, you just kind of go back to this expression here. You rewrite this as R times R minus 1 all the way through R minus K plus 1 over K factorial. So that K on the bottom still needs to be an integer or a whole number, like 1, 0, 1, 2, 3, so on. But R can be anything for this definition to work out here. Right. So, any questions there? And I guess just a little note here. If K is 0, R choose 0, this is always 1. There's always one way to choose nothing, essentially. Okay. So, let's use this to do problem 2. Right. So problem 2 is saying f of x is 1 over square root of 4 minus x. So we could, of course, find the Maclaurin series for this by doing all the derivatives and plugging that stuff in. But instead, let's use this binomial series here. Right? We call this the binomial series because this in here, this is a binomial, 1 plus x, and we're raising it to a power. So this is a power of a binomial is expanded in this way. Right? So actually, if R is a finite number, sorry, not a finite number, a whole number, then these eventually are just all 0. But if R is not a whole number, like if it's a fraction or something like that, then these go on forever. This will keep going. It's kind of neat. All right, so we want to express this as sort of a 1 plus x to the r. So first things first, write it as 4 minus x to the negative 1/2. And I'll give you a second to think about what we need to manipulate here in order to be able to use this. So I'll let you try that out for a second. So just like with the geometric series stuff we did, the most important thing is that 1 right there. So we need to make a 1 show up here. So we're going to do a similar trick to what we did for geometric series. If we factor a 4 out of these two terms, we get 1 minus x over 4 minus 1/2. And so this is, we factor that 4 out of there, so 4 to the minus 1/2. And here, I really want 1 plus something. So I'm going to write this as 1 plus negative x over 4 to the minus 1/2. Right. And then it's now at a point where I can hit it with that the binomial series stuff. So 4 to the minus 1/2, that's 1 over square root of 4. So that's 1/2. Then we have our series from 0 to infinity. Negative 1/2, choose k. Negative x over 4 to the k. And that's a series. Right, you'll probably want to make this look a little bit better. So say minus 1/2, choose k. Here, this will look better as negative 1 to the k, x to the k up top. Down here, we would have 4 to the k, but if we want to combine this 2, 4 to the k is 2 to the 2k, and then to combine this 2 in, we just add the 1. And there you go. And there we have it. There's a nice, good series. Right? And to compute these coefficients, we would just use this formula right here. So, maybe you look at this and you're like, I don't really like that. I want some actual numbers to look at. Well, there's not going to be any beautiful closed form thing to look at here. But if you were so inclined, you could swap these things out. Let's see. Do we want to write it that way? Yeah, probably the best way to do it is to just write out some terms of the series. It's like if we plug in k equals 0, remember this choose thing here, this coefficient's going to be 1. So you'll have, let's see, 1 times x over 2. That's when k equals 0. Plug in k equals 1. When you plug in k equals 1, the top of this is just going to be r. So this will be negative 1/2 times negative 1 times x over 2 to the third. Right? And then when you compute the next one, right, when k equals 2, you're going to get minus 1/2 minus 3/2, right? Because we take this and we subtract 1. That's going to be over 2 from the factorial here, times, well, this is negative 1 squared x squared over 2 to the 5th, and so on. Right, so it's probably not super interesting to write out the terms of it. This is, I'd say, the better way to look at it, but If you wanted to see a few terms, that would be what you would do. Any questions about this one? Oh, you can leave the 1/2 in front as well. That's fine. I would say let's see. For sake of looking at what the coefficients of this thing are, I think this looks a little bit better, though. I mean, this might be perfectly fine anyway. But I think doing something like this is probably a good idea. Just so you kind of know, like, what part really to really see like where the center of the series is and stuff like that. But I mean, it's a Maclaurin series, so you know it's centered at 0 anyway. I don't know. I guess this is probably fine enough, actually. Yeah, actually, leaving it there is fine. All right. Yeah, so there's quite a few different ways you can manipulate this and write it down. And the reason I kind of thought about doing this as an example today, the last example, maybe not the last one. I think actually it might have been number 6. The one with finding the Taylor series centered at 16 for square root of x. If you use this binomial theorem stuff on it, it actually works out a lot quicker. So I'll let you think about how that might work. But it's a neat example of a series we can write down nicely. All right. On that note, let's look at the next problem here before we get too far behind on this. So in problem 3 here, I want to find the sum of the series from 0 to infinity, minus 1 to the k, pi to the 2k, over 6 to the 2... Wow, I wrote to the 2 pi. To the 2k, 6 to the 2k, 2k factorial. Right. See if you can come up with the exact value of this series. What you got there? Any ideas on how we could compute this? Give you a hint if you haven't got anything yet. We look at it this way, it should remind you of something. Okay. So changing it to this form, what does that do? How can we use this to actually say what the value, the sum of this series has to be? Yeah, this is cosine of pi over 6. Right? Because if you look at this, if I swap this pi over 6 for an x, this is exactly the Maclaurin series for cosine of x. So since I have an x here, since I have pi over 6 here, that means I swapped x for pi over 6. So that means this is cosine of pi over 6. In other words, root 3 over 2. Right? So this is a neat trick we can use to find exact values of infinite series. Now, of course, it's a pretty rare thing that we're able to do that, right? We have to be able to recognize it as a power series for something. But the point isn't sort of how rare this is to apply. It's that, we're able to do it in certain situations, right? Because we're sort of hunting for, like, in what ways could we actually pull this off? All right. Let's look at problem 4. Might actually be able to fit that one here. So problem 4, we have the series 1 minus ln of 2 plus ln of 2 squared over 2 factorial minus ln of 3 cubed over 3 factorial, and so on. Any thoughts as to what the actual value of that can be? Your first step should be to try and write this in a condensed form. Where it's as a series like this. Bottom here is going to be k factorial. It's alternating plus minus plus minus. So you're going to have negative 1 to the k. And each time here, this is just ln. This is supposed to be of 2, not 3. Each time here, this just goes up in power. This is ln of 2. Okay. Any ideas yet? Yep, that's definitely a good idea. If you put this negative inside here, that will be a fantastic idea. So putting that -1 in there, what advantage does that give us? What can we see this as now? Yep, exactly. This is just e to the negative ln of 2, which we can get an exact number for, because it's 1/2. And there we go. Again, we can get an exact answer for these series here by trying to recognize them as, kind of known Maclaurin series or Taylor series with something plugged in. All right. Any questions about that? Cool. Let's go into problem 5 here. Right. In problem 5, what I want to do is we want to take various approximations of square root of 101. Okay. The question is, how do we do these approximations? Stuff out of here. Right. So this is sort of the subject of the last video in the series, in the lectures. Cutting off the Taylor series at various places gives us approximations of the function. So for example, if we cut off the series after x to the first power, then we get a linear approximation. If we cut it off after x to the second power, we get a quadratic approximation. And then, third power is cubic, fourth power is quartic, and so on. So what I want to do here is I want to use a linear, quadratic, and cubic approximation to approximate square root of 101. Right? Last semester, you might remember something about kind of using or doing linear approximations. You might have heard it called differentials, possibly. But basically, geometrically or graphically, the first degree Taylor polynomial is the tangent line, right? The second degree will be, it's not really a tangent parabola. It's kind of a parabola that fits as best as possible at a certain point. The cubic will be a cubic graph, a x cubed graph that fits as best as possible, right, at that point. And the place that sort of its tangent or that it touches at or that it tries to approximate near is whatever we call the center of the series. Right? So the idea to approximate something like this is we want to say, okay, let's let's take a Taylor series for whatever function this looks like it might come from, centered at a value that we can actually compute. Right? So this here looks like I took the function f of x equals square root of x and plugged in 101. So I want to approximate f of 101. Is there a value of x I can plug in to f that gives me a nice value that's really close to, or as close as possible to 101? what value would that be? I want to get as close as possible to 101, but still have a nice output from f. What x value would that be? Yep, exactly. So since f of 100 is really nice, and 100 is pretty close to 101, we're going to center our series at 100. So we want to center at x equals, or sorry, I want to say a equals 100. Okay. So since we're going to go up to a cubic approximation, what we need to do is compute the Taylor coefficients up through k equals 3. So we want fk of 100 here. So if k is 0, then the function is x to the 1/2, or square root of x. And f of that is 10, or plug in x equals 100, we get 10. When k is 1, we have 1/2 x to the minus 1/2. Plug this in, and we're going to get 1 over 20. Right? When k is 2, we're going to have negative 1/4 x to the minus 3/2. Plug this in, and it's I had this number earlier. Negative 1 over 4,000. Okay. And the nice thing here is, since we're not trying to make the infinite series anymore, simplify these numbers. It'll make your life a lot easier to work with this. Is that right? That's right. Right, and then 3, so this is going to be 3 over 8, x to the minus 5/2. Plug in 100, and we're going to get 3 over 800,000. Right? So these are the various derivatives with 100 plugged in. So now we want to do these different approximations. So the linear approximation, right? What we do here is we say, all right, well, f of x is approximately, so f of x is always approximately equal to its Taylor series when cut off at any point. So here, we're going to cut off, I'm going to leave a little gap here. We're going to cut off the Taylor series after the degree 1 term. Right? So this approximate equal sign here, this is true for values of x near 100. There's a way to measure how far out that approximation is, or based on how far you go out, what your error is. I'll let you sort of look that up in the textbook if you want. I won't kind of go too far into that here. But what I want to call this here, since this is the first degree Taylor polynomial, I'm going to call this T1 of x to just stand for first degree Taylor polynomial. Right? Then, f of 101, it's approximately the first degree Taylor polynomial at 101. Oh, sorry, I meant to do one thing first. This is equal to 10 plus 1 over 20 times x minus 100. Right, if we just plug in f of 100 and f prime of 100. Right, so compute this. This will be 10 plus 1 over 20 times 101 minus 100. So that's 10 plus 1 over 20. And this works out to be 10.05. Right? So again, this may or may not look similar, depending on if you remember this from last semester. But again, all we did here, the graph of, say, y equals this thing right here, this would be the tangent line. Okay? This is exactly the tangent line to x equals 100, or to f of x at x equals 100. So what we're saying here is that the square root of 101 is approximately 10.05. All right, so now we do this going on to higher degree polynomials. So the quadratic approximation, so f of x is about t2 of x. All right, it's approximately the second degree Taylor polynomial. Right, that's f of 100 plus f prime of 100 times x minus 100 plus f double prime of 100 over 2 factorial x minus 100 squared. Right. So let's plug in all this stuff, and you'll see we get 10 plus 1 over 20 x minus 100 plus let's see, what was this? This was negative 1 over 4,000. So this is minus 1 over 8,000 x minus 100 squared. Now, I chose square root of 101 so that these numbers don't work out too bad. But like if you wanted to approximate 110 or square root of 110 or 104 or something like that, right? You would use this same polynomial, you just plug in 104. Right? The approximation won't be as good as the 101 approximation is, but the higher degree you go, it sort of doesn't matter. You still get a good approximation. All right, so let's do this for 101. All right, so this is 10 plus 1 over 20 minus 1 over 8,000. Right, if you compute this, you're going to get 10.049875. Is that right? I think I did that right. Yes. Yes, that's right. Right. So for the quadratic approximation, we're saying that 101 is approximately equal to this thing. Right? And again, this is really the beauty of these Taylor polynomials is, you might want to try and approximate the value of some function somewhere, but it's something you can't really compute by hand. You can sort of approximate it with these more easy to compute numbers. So something to kind of point out here is like, this is how, say, a computer will estimate some things for you. But the other benefit of this, beyond just like, we could plug in square root of 101 into a calculator, right? But what if we don't have all the information about the function, right? What if, through experimentation, we're able to find out, what f of 100 is, what its derivative at 100 is, what its second derivative at 100 is. There's ways to kind of estimate these things using data. But, we don't have an actual function to work with. We just have like a discrete set of data. So we can use that, combine it with this theory here, and that'll get us nice approximations. Like if we look at this polynomial that tries to approximate the polynomial, or tries to approximate the function. So usually we're using it from the perspective of we don't know what f is, but we want to try and write down a function that represents f. Anyway, let's do the cubic one here, so we can finish this up. So I'm going to be a little lazy and just duplicate this stuff. Right. So for the cubic, we want T3, which means I'm running out of room here. That means we're going to want to add in the cubic term here, f triple prime of 100 over 3 factorial, x minus 100 cubed. All right. Remember, f triple prime of 100 was 3 over 800,000. So when we take that and divide it by 3 factorial, what we're going to end up with is 1 over 1.6 million. X minus 100 cubed. Right. So then, f of 101, this is approximately 10 plus 1 over 20 minus 1 over 8,000 plus 1 over 1.6 million. Right. And let's see here. Let's see, 1 divided by that plus 10.0487. Right, so this number is exactly 10.04987563. So the linear approximation was 1004. The quadratic was 10.049875. The cubic is 10.04987563. If we do this correct to 10 decimal places, which I did in Mathematica here, this is 10.0498756211. So compare these different approximations. Right? This linear one, oh, sorry, this linear isn't 1004, it's 1005. But still, that's not that far off, right? If we look at the quadratic one, this improves drastically. And if you look at the cubic one, we get some improvement. There's not a lot to improve on, depending on how precise, what precision you want, how many decimal places you want. But yeah, there's, these approximations, the better Taylor polynomial or the higher degree Taylor polynomial you use, the better approximation you're going to get, right? So again, if I instead wanted to estimate, square root of 107, you'll find like the linear one's going to be less good there. Well, all of them will be less good, but the linear one really is sort of good enough for most purposes. It's within 1/1000th. But, that probably won't be as good, but the cubic will probably still be pretty decent. Right? It depends, again, what kind of precision you're looking for. And I've already gone over time, so I think, wow, how did I finish problem 6 in the first session? Yeah, so I think I'll stop here. But I'll put up a short lab for Monday's class to just kind of look at this approximation stuff and try it for a few different values of x. A few different values. So compare the approximation, say at 101 with the approximation at 104, 107, 110, just see sort of how it's changing, right? And how, how the precision changes a bit. Yeah. Any questions at all there? All right then. Well, with that, I think that's our last problem session. So hope you enjoyed. Hope it was I mean, it's not the ideal replacement for normal on class or on campus classes, but hopefully these were helpful and useful in practicing and learning the material. And yeah, take care. Have a good weekend. I have office hours coming up in about 30 minutes. If anyone wants to, ask any questions, just let me know. Yeah, with that, I'll see you guys next time. Take care.